So the next question we've got with complex numbers is how do we represent them visually? I mean, real numbers, nice and easy. We've got a number line and we just place the numbers on the number line. So how do we do that with complex numbers? And it's through this idea of an Argand diagram. And it will look very similar to something we already know because it looks just like the number plane. But what it actually is the x-axis is what we're used to as the real number line. And then through the middle of that, we put a vertical one, which we call the imaginary axis. And then just like coordinates, we can plot individual complex numbers using their x and y coordinate or their real and imaginary values. So that way, every complex number will have a unique position on this diagram. So as I say, the horizontal axis we call the real axis, the vertical axis, the imaginary axis. In fact, some books you might even see them labelled, instead of x and y, you might see them labelled as in real z and imaginary z. Sometimes you'll see them labelled that way. So if I want to plot the number 2, well, same as normal. 2 is a real number. We plot it on the number line. There it is. Minus 3i, something that's purely imaginary then, will be on the imaginary axis down at -3. But of course, most complex numbers are a mixture of the two. So minus 2 plus I, well, minus 2 on the real, 1 on the imaginary. So no different to just plotting coordinates. 4 minus I, there it is over there. Its conjugate, this then brings up an interesting feature. Conjugates then should always be reflected in the real axis, because the only difference with a conjugate is the sign of the imaginary part. So any number that's reflected in the real axis, they must be conjugates of each other. Okay. Now, f is the point, the negative of 4 minus I. So in other words, negative 4 plus I. So if I want to find the negative of a complex number, and I'll plot f over there, then there again is some symmetry here. This time it's not reflected in the real axis, but it's reflected through the origin, if you like. Imagine drawing a line from D to F. It'll always go through the origin. So opposites, another way of thinking about it is we've just rotated that point 180 degrees. Again, DF creates a straight line or 180 degrees. So if I multiply by I instead of -1, this is what I was talking about the other day, you might remember, is we can think of it as rotation of 90 degrees. And so it will be up there. So G turns out to be 1 plus 4I, but again, a way of thinking about it is if I got the point D rotated at 90 degrees, okay, so anytime you multiply by I, you end up with a 90 degree rotation. Multiply by -1, you get a 180 degree rotation, because that's two 90s. I suppose we could carry on from that and say, well, multiply by -I, we get a 270 degree rotation. So, as I say, every single complex number then will have a unique position on the Argand diagram. So no point would represent two different complex numbers. So now we can talk about this idea of locus, but we can put it in terms of complex numbers. So a couple of simple ideas. If I was to draw a horizontal or a vertical line. So there's a horizontal line, whereas before we would have simply said, oh, it's got the equation y equals c, which is true. But if I'm talking about features of every complex number, what do they have in common? It's their imaginary part is always equal to c. So if we get some sort of locus question where they said, look, we want you to plot every complex number such that their imaginary part is always equal to c, then we know we're talking about, oh, a horizontal line must go through c. So a vertical one, well, all those complex numbers would have that their real part's the same. So they're the most basic straight lines, I guess, is horizontal and vertical. We'll worry about ones at an angle later. Circles also are quite interesting. There's our circle. Remember, we said z times z conjugate was x squared plus y squared. We also know circles are always in the format x squared plus y squared is some constant number. So if we have a number times its conjugate, and we want all of the numbers such that the answer is r squared, we must end up with a circle, because we're saying x squared plus y squared is the radius squared. And so every single complex number on that circle, if we multiply them together, we'd end up with the answer r squared. Okay, so we're going to find and describe the locus of these points in the actual Argand diagram. Ooh. Z plus 4 plus I, conjugate of Z plus 4 minus I is 49. Well, again, it's the same idea. We are actually saying Z times Z conjugate is the radius squared, but we've got some shift happening here. Because instead of just saying Z, it's Z minus something. If I was to expand the whole thing out, you'll see what ends up happening. So I'll expand the whole thing out. There's the Z conjugate multiplied together. So that's the x squared plus y squared that we want. If I was to keep going and substitute in eventually for Z and Z conjugate, x plus iy and x minus iy, we would end up with this equation, x squared plus y squared plus 8x plus 2y plus 16 minus, about plus 1 is 49. It looks like a heck of a lot of working out, and it is if you do it that way. Let's tidy it up, completing the square on these. So I'll group the x squared with the 8x and the 2y with the y squared. Remember, we add half the coefficient of x squared. That's the idea of completing the square. So this could become x plus 4 squared plus y plus 1 squared is 49. We now know what that is. That's a circle, centre, minus 4, minus 1. Let's go back to the original question and have a look. Z plus 4 plus I, conjugate plus 4, that's also the conjugate of 4 plus I. So I don't need to go through all that. If I see it, it's in the form Z conjugate, but also the number that we've added to the conjugates in the other one, I know that's going to be a circle. I've just shifted it to, in this case, 4 plus I, or the point, sorry, because it's always Z minus the centre, minus 4 minus I should say. Unusual way of seeing it, but I mean, they could ask us that. As I say, you can save yourself some time if you realise that relationship. You don't have to end up expanding the whole thing out and trying to go, oh, what's the equation of this one? What we're saying is if you see Z minus some complex number, and then in the other one you've got the conjugate of Z minus the conjugate of that same complex number, then that will be a circle, centre, omega, whatever complex number you're subtracting, radius r. That's the pattern that you're looking for. Let's have a look at this one. 1 on Z plus 1 on the conjugate of Z is equal to 1. Now, if you don't recognise it straight away, you can always go back to, all right, I'll sub in x plus iy, and that's going to end up giving you a Cartesian equation, because remember we're using the number plane in the Argand diagram, basically the same thing. So if I bring x and y's into it, I can always come up with a Cartesian equation. But I've decided to play around with it a little bit. I'm going to multiply, if you get rid of the fractions, so I'm going to multiply by z conjugate. And I end up with z conjugate plus z is z conjugate. And these are things I now recognise, because you remember a number plus its conjugate will get 2 times the real part, so it's 2x. And we know z times z conjugate is x squared plus y squared. So by getting that little pattern, save me a little bit of time. I mean, you could have substituted in the x plus iy at the top. You would eventually end up with the same answer. So I know it's a circle, because there's my x squared plus y squared, but let's group it and complete the square. There it is. X minus 1 squared plus y squared is equal to 1. So we know we've got a circle, centre 1, 0, radius of 1. There's the picture right there. That's what it would look like. So every complex number on that circle satisfies that relationship. Excluding the point 0, 0. Remember, with locus, sometimes we have to look for points of exclusion. Why would I exclude the point 0, 0 from this circle? Yeah, because look at what the original question was. The original question was 1 on z plus 1 on z conjugate. Well, if I'm talking about the point 0, I can't substitute that in because I get 1 on 0. So it'd be every other point on the circle would work, but not that particular one. Okay.